Let's look at an application of a level curve. Suppose we have a function t of xy, which is 40 over 1 plus x squared plus y squared, and that represents the temperature at the point x comma y. So find and interpret the level curves associated with c equals 4, c equals 10, 20, and 40. All right, I don't know if I'll do all of those. I think I might just do some of them. All right, so let's look at c equals 4, for example. All right, that means that 4 is equal to 40 divided by 1 plus x squared plus y squared. All right, well then if I multiply both sides by the denominator, 4 times 1 plus x squared plus y squared is equal to 40. That would mean if I divide both sides by 4, 1 plus x squared plus y squared is equal to 10. Subtract the 1. X squared plus y squared is equal to 9. All right, so that's a circle. Right, that's a circle of radius 3 centered at the origin, of course. So let's see, if this graph, if I go 1, 2, 3 out, 2, 3, 1, 2, 3, 1, 2, 3, and I do my best to draw a circle. They won't always be circles, but circles are interesting for us. And they're also pretty easy for us to draw. There we have it. All right, so now let's do c equals 10. All right, so 10 is equal to 40 over 1 plus x squared plus y squared. So if we do the same trick, multiply by the denominator, divide by 10, you'll end up with 1 plus x squared plus y squared equals 4. So then we subtract 1 from both sides, and we'll have x squared plus y squared equals 3, which is a circle, and the radius is the square root of 3, which is about 1 point. Hold on, I think it's 1 point. No, I was wrong. It's 1.7. I just did that one. I just forgot what I'd done. All right, so 1.73. All right, so let's see here. 1.7 is kind of right about there. So I'm going to draw a circle. All right, let's do 20. I think I can fit 20 in. I don't know if I have room for 40. So c equals 20 would be 20 equals 40 over 1 plus x squared plus y squared. So that would mean divide by 20 and multiply by that. 1 plus x squared plus y squared equals 2. So then x squared plus y squared equals 1. So that's a circle of radius 1. Oh, r equals, just to keep it consistent with the others. All right, circle r equals the square root of 1, which is 1. So that's right here. And I take it back. I will try to fit in the 40. Let me just sneak it in over to the side over here, because I think you see what's going to happen here. So if I say, if c equals 40, if I say 40 equals 40 over 1 plus x squared plus y squared, when I divide by 40, that's 1. So you're left with 1 plus x squared plus y squared equals 1, which means x squared plus y squared equals 0. It's a point. It's the origin. So that would be that dot right there. All right. Now, what in the world is this showing us, right? So we found the level curves. What are we seeing? So what we're seeing is that, right, as we let the temperature, that's what this is, temperature, T, equal to these different values, right, we can see that there's a ring of that temperature kind of built around the origin, right? And the farther we get away from the origin, the less steep, if you will, that curve is going to be, because these curves aren't packed so tight together. So all of the points along that ring, right, xy, all the xy's on that ring where c was equal to 4, where we set the temperature equal to 4, they all have the same temperature of 4, right? And then they are only 4, but as I get closer to the origin, my temperature's higher. C equals 10. then, right? And then higher and higher. The closer I'm getting to it, the faster the temperature is rising. So in other words, it's cooling as I move away, and it's rising as I go closer. And it's rising faster and faster because the rings are tighter together. And also, this must be the heat source. The origin must be the source of heat because the rings, all the rings are concentric around that origin. So all of the dots on the pink ring have the same temperature of 10. All the dots on the blue ring have the same temperature of 4. Sorry, this is temperature. so, so imagine it sort of like the burner on your stove, right? That's the central point of the burner, and then close to the burner you have high heat, and then it moves away in concentric rings to cooler and cooler temperatures. So I just kind of wrote that up a little bit. So it's hottest closest to the origin, right? It's hottest and growing fastest. I should add hottest and growing fastest because the rings are closer together. Right? And then it's cooling in even rings as we move out. And by that I just mean as you go to the ring, I don't know if I should use the word even, but it's the temperature is the same all the way around. I guess I won't use the word even because they're not even. They're actually closer together as we are close to the origin and farther away. So cools away in concentric rings. I'll just say that as we move away from the origin. Now, oh, and I should say all the points on a ring have the same temperature. And I do think it's easier to see in Maple, although I don't like this particular graph in the thing. Let's see if we can look at it. All right, so there it is, right? And I did, again, surface contour, so we could see the contour curves that we are then casting the shadow of down onto the XY plane. So there it is again, right? I did a plot 3D graph and I did an implicit plot 3D graph. I like them both for different reasons. So the thing about plot 3D is you have to remember there's no z equals on this one, and there is a z equals on this one if you're doing it with z equals. And you can see, I didn't do the contour plot, but you can see those concentric rings, that's the shadow you're casting. So the source of your heat is at the origin, and as you move further away, right, as you're close to the origin, the rings are tight together. And as you move further away, they're getting farther and farther apart because it's getting cooler and cooler, right? And it's not rising, or the temperature's cooling. And as you get close to the center, it's rising faster and faster, right? And we all know this from being anywhere close to a burner in a kitchen, that's how that works. So on our paper, if we want to say there are concentric rings, it's hard to see them though, but that's what you're doing, right? So they're tighter, closer together than they are down here. That's all. But I will say that the three-dimensional graph is all well and good, but the two-dimensional graph actually kind of helps us represent steepness better because we can tell the rings are close together versus farther apart, right? And of course we can see that when we tilt the graph, right? When we look at it this way, it looks like they're all even. But when I tilt it this way, then you can start seeing that they're tighter together. So the two-dimensional graph actually represents steepness in a way better than the three-dimensional graph. Right, the three-dimensional graph, your eyes can deceive you. But when you look at it this way, you can see the rings close to the origin are tighter together than the rings farther apart. And I just wrote that up right here. So the 2D graph is actually doing a better job than the 3D graph at representing steepness. That's why topographical maps are so useful. Oh, sorry, my word there was driving me nuts. Okay, so the 2D graph represents steepness better than the 3D graph. And the way it does it is by the closeness of the rings. So when the rings are close together, that means it's steeper than when the rings are far apart. And that's much easier for us to gauge visually than a 3D graph, which requires us to move it around and change our perspective so that we can gauge steepness.